Well, it looks like we're just about there. Welcome back, everyone. And it's now official. Looks like we can get started. We're now on week 13. I think I forgot to put that on there. Not that it's super important, but it's just exciting to see that we're getting pretty close to the end at this point. Our goal for today's class is finish up chapter 20. We're on the last example 4 on there. It's a technical problem where we're doing a hypothesis test with 2 proportions. So the major work before we got to example 4 was just seeing how the methods change with this new hypothesis test. Excuse me. After we finish off chapter 20, we're going to start taking a look into chapter 21. This is going to be the final chapter for the entire semester. And I didn't immediately put down an assignment set because we're now getting across exam 3 close to the point at which we're going to release the final exam. Final exam is going to be released as a take-home exam on Thursday of closed week. So that means it's going to be released on, let's see, not the 24th, that's an ordinary week. We're doing an exam on the 22nd, but we're going to be releasing it on the 1st, looks like, to be due on the 8th of finals week, I believe is the plan. I think we actually said the 9th, so we'll keep that official. I don't want to necessarily release another homework assignment and get it all jammed up with the take-home final exam. So depending on where we end up with chapter 21, probably what I'll end up doing is not post an extra homework assignment, but rather on the actual take-home final exam, I'll probably indicate which one is the chi-square procedure. Since we didn't have the extra practice on it, you would just be redoing kind of what we did in the notes, kind of like just an extra homework assignment, but only one problem attached to the final exam. So that's going to be our goal for the last 2 chapters that we're looking at here. Nearly done with one, and not a whole lot of time to completely finish this one off with a homework assignment. But aside from those elements of the announcements, the next exciting bit is we have our next exam a week away from today, next Tuesday. This exam is going to have coverage on chapter 17, 1 population mean, chapter 18 on 2 population means, and chapter 19 on 1 population proportion, only because we didn't quite finish off chapter 20 last week. So there'll be 3 chapters, expect between 3 to 5 problems altogether, probably around the neighborhood of about 4 like the other exams. I'm a little bit behind this week, I have to admit to you. I haven't quite written this exam yet, but I intend to make that my first thing I'm going to be doing on Wednesday morning. I'll get the exam written up, I'll be proofreading it, and once everything is finalized, I'll send out the information to people who test in the Pocatello Testing Center, so the Zoom side of the class. And our class for the in-person side will just take the exam as the traditional one like we've been doing on Tuesday. So that's our plan so far. Other things to mention, just like we had the opportunity to on exam 1, exam 2, also on exam 3, when we come back on the 17th, Thursday of this week, any questions that folks have on exam 3 material, I'll be happy to take. I mean, really any question. We always start off the class with questions, usually after the announcements. So I'll be happy to make next Thursday, the 17th, kind of an impromptu review day. Any questions at the moment so far?
Is the final mean like or the whole semester?
Yeah, absolutely. So it's going to cover, well, that's a great question, actually. There is certain areas where it's emphasized a little bit more, so I'm glad you asked that question. We go back up to the very top, we won't have as many questions directly from chapter 1, because actually the purpose of chapter 1 was look into the differences between quantitative, categorical data, and really actually just playing around in RStudio, getting used to it. So probably no direct questions at this chapter. You still need to know this information because telling if your data is categorical or quantitative directs you into the right statistical procedure. Chapter 2 is a little bit different as well. I don't think we'll ask a direct question from chapter 2, only because the role of chapter 2 was just to show how to produce graphics with RStudio. So you'll use chapter 2 indirectly to produce histograms or box plots to determine if your data is heavily skewed, conditions are met, that kind of thing. Chapter 11, we won't directly ask a question out of this one either, only because we only needed chapter 11 so we could get p-values out in a rapid way. I would say the exam as a take-home final exam really is going to start in chapter 13. There'll be a question that is similar to this one, using the central limit theorem in a type of what-if analysis. We've done a couple of these. So this is a problem where, let's see, no sample has actually been collected. We're just analyzing the central limit theorem to say what could happen to the sample. What's the odds of it being between specific bounds, those kinds of things. So there will be a chapter 13 question. Chapter 14, we're going to skip as well because this was a practice section. It was a full-on introduction. The methods weren't really solidified there. We were just introducing what is a confidence interval in the first place, what is a hypothesis test, and how to write them. Chapter 15, however, you can expect a problem. Chapter 15 might have a two-parter problem where you're coming up with the sample size to target the right margin of error. And a second problem might be doing something along these lines. Sorry, it takes a moment to get to these notes. I forget how big they get when we finalize them. Another problem might be something along example 4. We're saying what a type 1 error is, what a type 2 error is, then analyze which error might be more concerning. I might ask you to select a significance level alpha, depending on how concerning you feel the type 1 error is, and then maybe do a power analysis. Already that's a pretty big question, so I might have to walk that back a little bit and kind of shorten it up. But those are the things that could happen in chapter 15. But then when we go down the line, it starts to get a little bit more clear. You can expect either a hypothesis test or a confidence interval in chapter 17 with one mean. Whether it's a hypothesis test or a confidence interval is essentially selected by random. I'll be doing that in each chapter, but if I get all hypothesis tests, I'll randomize again to make sure there's an actual equal weight of confidence interval methods and hypothesis testing. So then again, chapter 18, expect just one method here, either a test or an interval. Same with chapter 19, chapter 20. And our last one we'll give hints on because this one we're not quite in the position to do homework, have it graded, get it returned in the short amount of time we have. So one question from this chapter as well, but it'll say use the chi-squared procedure. So the thing that might sound concerning about all that is there's not direct guidance on to use the methods in chapter 20, chapter 19, chapter 18. We have to come up with that on our own. We have to select our own method. So that's going to form our big part of what we're reviewing on in closed week. To really make that a fair problem, we need to do it ourselves. So I'm going to have a practice exam that we'll do as just a kind of like a dress rehearsal of the final exam. So it'll be very similar, same number of questions, same kind of problems, but it's going to be scrambled. So we'll do the important work of untangling it, determining which method belongs to which problem. At the end of Thursday on closed week, that's going to be the 24th, I'll just unhide a document that it will be the actual take-home final exam. And you'll do what we just did in class over this entire week with a new set of problems. So that's going to be kind of the idea. I'm going between, I think I probably said about 8 to 10 problems when I verbally said them out. But I'm really going somewhere between 6 to 8 problems altogether, not trying to make it too long. But other questions about that so far? Either the third exam or the final exam? We're pretty close to both of them, it turns out. Okay, well, other announcements are just the exam 3 material that's posted down below. Just like before, I'm a fan of parallelism, so this is the exact same type of content that you saw in exams 1 and 2. These are the actual lecture notes as worksheets. They form a really great base for doing these kind of problems. And some information like this is baked in just to make it feel like what a real exam is going to look like for us. You'll have to know how to work the formulas, but anything that had to be computed through like RStudio or a TID4 calculator, anything like that, is just provided on the exam. So you'll definitely want to take a look at the exam 3 formula sheet as you study. This will tell you everything that's provided, and make a mental note as you study. If there's something that's not provided that you really needed as a formula, it's meant to be a formula that we had to have in our mind, something memorized as part of our preparation for the exam. The core formulas are all here. So things that could be missing are just small concepts, really. So we have the statement of the test statistic here, the full-on method for the confidence interval. Same for the 2 sample methods. We have the confidence interval and the test statistic. That's weird, I kind of scrambled the order there. Degrees of freedom formula is here as well. So I'm going to have to control the length of the exam so we can have time to run through this. This is the point at which I'd probably give a reminder. Don't forget when you do a paper exam like this in class or in the Pocatello Testing Center, as a concept exam, you have to put in this information to your calculator to get a number out, but write this all down on paper. That way, if anything goes wrong with the calculator, any order of operations glitch, anything like that, if it's accurate on paper, I'll still give full credit to it. And same for any other method like confidence intervals, test statistics, standard errors, and so on. Same comment will apply. Then down below, this is the chapter 19 methods. Same kind of information, the statement of the confidence interval, the statement of the test statistic. So take a look into that document, either one here, but definitely have this one pulled up as you study. And this one is brand new problems. We have really 3 sets of problems. Lecture notes here, the homework exercises that you yourself solved are very powerful and helpful for studying. But if you want just something fresh and new, these are the new problems. I wrote these out last weekend, so I don't have the solutions yet. But when I go into Friday of this week, my goal is to start solving these and get solutions posted. After I do that, I'll convert into grading the homework problems, particularly the ones for these chapters, so I can make sure I get them returned to you as an extra resource. So that's our plan going into exam 3. And I guess that fills out our announcements. This was a longer set of announcements, 11 minutes almost. Any questions at all, folks, so far with any of those announcements? Or any questions so far before we start out, just in general? Okay, let's get back into where we were, chapter 20. We were looking into a hypothesis test for 2 proportions. The hypothesis test for 1 proportion is already pretty tricky. You'd want to very carefully look into the formula on that formula sheet when you run it. But 2 proportions is something entirely new altogether. Let's take another look at this just as a warm-up before we delve deeper into the notes. In this particular section, we have categorical data we're analyzing. 2 categories, meaning just as successes or failures. But we're also studying 2 independent populations at the same exact time. So now we have 2 parameter values. P1 is the proportion of successes in the population for the first population. And this is the true population proportion of successes in the other independent population. We want to ask the question, are they not equal? Is one bigger than the other? Is one lesser than the other? This one's formed as a 2-tailed test. So to analyze this hypothesis, the very first step is we assume the null hypothesis is true. That assumption allows us to create a 3rd variable, P0, which is equal to both P1 and P2, because that's the statement of the null hypothesis. Your populations are the same now. What that allowed us to do was take the central limit theorem right here from the very, very top of the notes for the differences in proportions. So let's call this central limit theorem, CLT, for P1 hat minus P2 hat. This is its sampling distribution. But now that P1 and P2 take a common value P0, it becomes a 0 down here. The next thing that happens is the standard deviation in this position right here takes on a new format. P1 is P0, P2 is also P0. So the numerators are the same and we factor it completely out, leaving the reciprocal of the sample sizes over here in the second factor. So this is the new central limit theorem, assuming we're running a hypothesis test, and we made the assumption, as we have to in this test, that the null hypothesis is true. It becomes that, and from there, we now pool our proportion of successes in both samples to estimate P0. P0 is the value for P1 and P2 at the same time. So we go and redefine P hat. It's going to be the successes in the first sample, the successes in the second sample, both sample sizes pooled together. And this is a natural thing to do because the null hypothesis said the populations were the same. Therefore, both sample proportions of successes, P hat 1, P hat 2, are estimating the same value, and it gets pooled this way. I'm noticing a weird way I wrote the standard error, however. Let's make a fast correction. I'll call this standard error P hat 1 minus P hat 2. Let's make this pop with a red tone color. This is better described as standard error, p hat. But it takes the assumption, this is now context sensitive, very context sensitive. P hat is not your chapter 19 p hat. This is the pooled sample proportion of successes in chapter 20. Better still call it standard error p hat. Takes on this formula, inherited from up here because p hat is now estimating p naught. Let's write it this way though. Usually we wrote our estimate this way. So everywhere p naught was, we throw in p hat, and this is going to allow us to now finally do a hypothesis test, because the test statistic becomes the difference between the sample proportions of successes divided by the exact standard deviation. Well, the approximate standard deviation rather, using p hat to estimate the p naught right up here. So it's still an approximation here, and we can say that this quantity is the approximate number of standard deviations that p hat 1, p hat 2, let's say it slightly better, that p hat 1 is away from p hat 2. I need to find a better way to switch these colors. That could really speed this up, but thinking about it again, I don't know if there's a need to write as fast as possible in every single situation either. So there we have it. That test statistic will allow us to now get a p-value out. And we get the p-values in the same exact way we would have in, say, chapters 14, 19, and now 20. In other words, we're just using the normal distribution again. Well, any questions, folks, with that quick rundown of the methods for chapter 20? Okay, with these methods in play, let's take a quick look at the full statement of the test. So here we are testing the null hypothesis P1 equals P2. We assume that the null hypothesis is true. And right here, it's just a statement that that's an assumption the populations are now identical. And so we should pool the sample proportion of successes. Here's the formula that we were looking into. X1 is the successes in the first sample. X2 is the number of successes in the second sample. And so now we have one common estimator, p hat. A dangerous little structure there, because always remember, this is not the p hat in chapter 19. So our actual symbols that we use to denote these things are really overloaded. They have become highly context sensitive right at this point of the course. But if we know what context we're on, we'll know which p hat we're always thinking about. Next, for the actual test itself, we have to have two simple random samples from two independent populations. This is the statement that we briefly discussed. And now, huge departure from chapter 19. In chapter 19, the part 2 right here, this is something we carefully check. It was looking for a number of expected successes in the sample, not the actual number of successes and failures in both samples, like in this chapter. But this is wild. Condition checking is very, very tricky when you're looking into categorical data. The context, slight shifts like this, make the way you check very, very different. This is different enough. We should take a look into chapter 19 just really briefly. So in chapter 19, the related method looked like this. Once I get the windows to behave, I forget this doesn't open up Adobe, this just opens up a new browser. So we're checking conditions on a hypothesis test just to see the methods. And here we go. When the null hypothesis is true, we're just directly using the original central limit theorem. And we used these values, greater than or equal to 10, greater or equal to 10. But these were the expected number of successes. That means we took n times p naught, the value that came from the null hypothesis right here. It's weird that we couldn't redo that method, but when we think about it, it might make a lot of sense. we can't find the expected number of successes down here. We're using the literal number of successes and failures in the sample, and that's because we don't know what P naught is. Coming up here, in our null hypothesis, we make the statement only that they're equal. We didn't assign a value to it, we just said they're directly equal. In chapter 19, you do assign a value. You say P equals maybe 0.35, and that gives you now a number to feed right into the central limit theorem. And these are just the statements from the central limit theorem directly. But here, sure, we could set P1 equal to P2 equal to P naught, but our methods don't allow us to say a literal value for P naught. They're actually pretty restrictive when you really look into how far these methods can go. So because of that loss right here, not knowing P naught, we cannot use the expected number of successes. This is going to make it a larger sample type of problem. We want successes in the sample, let's say P hat, not P naught this time, to be bigger than 5, failures in the sample to be bigger than 5, and this applies to both samples. So here's the second indexing, samples 2 and 2, proportion 2, P hat 2, also bigger than 5 on both ends. So if we can meet that benchmark, then we expect the central limit theorem to be accurate for us and be just as effective. Last thing, this is the part where we say not required to discuss. But it's mostly here just for the sake of completion. Same with really all of our methods, even in chapter 17 with quantitative data. We use the central limit theorems, which assumes a population has infinite size. That's essentially a lie on every single problem we're looking at. Almost all of our populations are finite as a rule. But the central limit theorem is still effective if we break that and assume our population is finite, provided the population is so large that the sample, in its smallness by comparison, allows the central limit theorem to still feel like it's dealing with an infinite population. The rule of thumb is each population should be at least 10 times larger than the sample. Sample size can't exceed 10%. And it's the same kind of assumption really for any method that uses the central limit theorem. It's just not always stated directly in the formulas like this, but it's a good thing to state. Just as a reminder, there's always a limit to our methods. But finally, getting through the condition checking, we calculate the test statistic through that version of the standard error. And this is just a readout of the same methods from p-values. Again, chapter 14, chapter 19, and again, chapter 20, same exact kind of methods. Well, we'll put this into action, calculate a hypothesis test, and then move to chapter 21, where we're still dealing with categorical data, but now we allow for 3 outcomes or more. So not a dichotomy, successes versus failures. Any questions at all about the methods before we put them in action? Okay, here's our problem we're going to give a try. We briefly took a look into this problem, and it's a wild one because the data that we're being given is really hard to think about in terms of randomization and independence. These data might not actually meet the conditions, but let's run through it and see exactly what's going on. The fun thing about these data is it's biological data. It's a real hypothesis from biology. So it's a fun problem all in its own right. Here's the statement of the hypothesis itself. In the study of evolutionary behavior, the Trivers-Willard hypothesis indicates that healthy parents should tend to have more male offspring than female, that the weaker parents should tend to have more female offspring than male, and this tendency may maximize number of each parent's grandchildren and thus help to ensure that its genetic code is preserved. Since a healthy male offspring can win many mates, but a relatively unhealthy offspring has the best chance of mating if it's female. So that's the statement of the hypothesis. It takes a minute to read that and reread that to kind of get a feel for what they're trying to indicate. Let's indicate or just highlight this one part. Indicates that healthy parents should have more male offspring than female. Everything after that is a justification of that hypothesis. But let's just zero in on this one part right here. This is part of the course in statistical methods anyways. a lot of times we're overloaded with too much information, and it's our job to kind of try to sift through it and find the relevant part. That's the big part of the hypothesis that we're about to test. And down below is how they're going to look into this in a particular experiment. This is a pretty weird experiment, though. They say, in an experiment to examine this hypothesis, you have a group of 40 opossums. They're going to be monitored. 20 of them were given an enhanced diet. And you might think the other 20 are given some other diet. What does that say? Enhanced diet. Without the enhanced diet. So I guess just a regular diet is what they're saying. But notice they didn't take 20 opossums, give them an enhanced diet, and another 20 possums and give them what would we say, just a greatly diminished in quality kind of diet. That kind of animal study would probably never, ever be approved. So we're giving one group just the regular diet for opossums. It's a great diet, we're going to assume. And the other 20 are just being given the royal carpet treatment. They're getting just extra, I guess, enhanced in a lot of different ways. But then this is what they do next. This feels like a nice experimental design where by randomization, we hope that 20 of them get the enhanced, the other 20 get the regular. But these 40 opossums are not directly used in the response because we're looking into the offspring, right? That's the big part of this. So here's what happens next. After a certain period of time, the opossums with the enhanced diet had raised 19 male offspring and 14 female offspring, and the opossums without the enhanced diet, 15 male offspring, 15 female offspring. That means 40 split into 2 wasn't our sample size in the first place. We're looking into a new sample on the offspring and looking into this condition where it looks like the hypothesis is all about more male offspring. We'll consider the males then to be the successes in the samples. But this might give us some really strong worries about how would you justify the sample was reasonably randomly selected, and maybe more critically, are the individuals in the samples independent from one another? There's a lot to resolve here with randomization, which is sometimes kind of unfortunate because a good experiment in contexts like biology does require some cleverness, some thinking outside of the box. Sometimes you really do get your data in a very roundabout way. Now the experts have to analyze the methods and either justify the randomization or attack it. Depends on whether, that's going to heavily depend on whether this would have been published in the first place. So let's start breaking this down based off what's been said in this paragraph here. We have an enhanced diet. This is a good problem to just really get some scratch paper out, put information on the margin, or if you're using a digital file like this, just reformat it, put in your analysis of everything going on. We have an enhanced diet, and then we have, let's just call this a regular diet. In the enhanced diet, we have to count the number of successes. So let's see here. After a certain period of time, the opossums with the enhanced diet raised 19 male offspring. So we'll call that X1, 19. 14 female offspring from over here. Just as important, that gives us now the total sample size. Sample size N1 is going to be the number of successes, 19, plus the number of failures, 14, which gives us altogether 33 as the total sample size for N1. Now we have to do it again over here, but might not be a bad idea thinking about how we have to go through these data. Let's calculate, sorry, I don't know what I'm doing with my colors there. Let's calculate p hat right here. So p hat 1 is going to be x1 divided by n1, which is then 19 divided by 33. So this is the breakdown of the first population with enhanced diet. We ended up with 33 opossum offspring. So our sample size we might have expected is not what is actually happening in this problem. Now we do it again. So X2 is going to be the number of successes for the opossums given the regular diet. let's see, opossums without the enhanced diet, so that's our clue in, different population, raised 15 male offspring and 15 female offspring. Using that information here, let's call X2 15. N2 for the second sample size is now going to be the 15 plus the other 15, but selected in that exact way, follow the color coding. So sample size 2 is 30 on this one. And finally, our next statistic, p hat 2, is going to be number of successes, 15. Guess we can write out like before, X2 divided by N2. So that'll be number of successes, 15, divide by sample size, 30. And kind of nice for free, this one reduces. Might as well take advantage of that just to make everything else a little bit easier. We get exactly 1/2 on that one. This one's closer to maybe 2/3, so that might give us some evidence that this is a correct hypothesis. But we know better than that. We have to take into account that there's randomization, that there's variation in data. The values of the statistics p-hat aren't the full story until you start to bring in standard deviations through the standard error. But this is our read through of the problem so far. Any questions about it at the moment? Anything that we kind of missed here? Okay, let's now go off to the next phase. We need to describe unknown parameters. We indicate statistics p hat 1, p hat 2. Then all we're really doing at this stage is saying let p1 and p2 be the population or portion of what we put in the next step is the successes in the problem. And the way the hypothesis was stated, and the way we shaded this, and in particular the way they just gave the data itself in the statement of the problem, they're indicating the successes should be the outcome of a male offspring. So we'll say P1 and P2 denote or be the proportion of male offspring to, I'm really not too sure on this biology context if I should be saying opossums or if I should be saying possums if they're the same or different. I have a feeling they're different, so I'll just keep on saying opossums. So the male offspring to opossums. Now at this point, we're mentioning the population. Well, let me say that in a better way. There's two populations. We're mentioning the populations. But in a certain sense, we're really just mentioning the experimental design. There are two treatments to the parents of the offspring. They are randomly selected to go either into the enhanced diet, 20 of them, or into the regular diet, 20 of them. And because we're dealing with offspring, we just have to accept they're probably going to be dealing with unequal sample sizes like we saw here. So we'll say to finalize this, to opossums given a, we're going to use the respectively little trick there. If I indicated P1 first, I have to mention enhanced diet first. Let me say given to make that feel a little bit more grammatical, given an enhanced diet. And across and we're on this part, matching the parallelism. We mentioned P2, which is just discussing regular diet and regular diet respectively. And we've got it. That's the description of the parameters. Any questions about getting those nailed down so far? Okay, next bit is the null alternative hypothesis. Hard to know what to screenshot here, so maybe this part, that's the statement of Tribber's-Willard hypothesis in the first place. And the question was asking, does this finding, the data that we got, provide evidence in support of the Trivers-Willard hypothesis? So the alternative hypothesis should be captured somewhere through the statement here, the statement of the hypothesis itself. So let's think about that, state our null and alternative. It's got to be a statement that involves P1 and P2 in some way, somehow. We're talking about the parameter values. Let's write out. We will test H naught. The statement for the test for H naught, well, there's kind of a trick to this, or maybe it better said it's sort of a freebie. The null hypothesis for chapter 18, two population means, and chapter 20, two population proportions, always goes essentially the same. It's more restrictive than we kind of let on. It's that P1 equals P2, and it stops right there. We don't assign it any value. We're just saying it takes a common value. Who knows what it is? It would take more work to say it's some specific value like 0.72. So we're not quite running that test, but this is a test that we can run based on the methods we have. We'll say test that null against, or versus is a good word there, the alternative hypothesis statement. Here's where we have to take the essence of what was being stated there and write something. There's still going to be a P1, P2 like before, but really our job is to decide for what goes here, is it less than, is it greater than, is it not equals? Any volunteers for the right test we'll run on this one? Yeah, I would agree with you, absolutely. The hypothesis says healthy parents should tend to have more male offspring than female. And you know what? Both parents were healthy on this. So again, people might complain about this experimental design. Why not put restricted diet right here? That would show the separation of the data a little bit better, but it would become unethical in animal studies. Really, any kind of study like that, using living things, that is usually a bad direction to go in for sure. So we allowed this diet to be a regular one. And when we say healthy parents, we're just hoping that the 20 opossums here are now more healthy because they've just been given the royal carpet treatment now with the enhanced diet, maybe extra granola inside that diet, something like that. We hope that that's enough to show more male offspring, that's the successes for the healthier parents through this hypothesis. That means, exactly as you said, we should have a greater than direction here, forcing this one to be a right tail test. And like we mentioned before, if we're not sure, if there's any kind of hesitation, if you feel like it's just a better test, put the two-tailed test here. The not equals is always a default. If we find information that flips us to a greater than or less than, that's excellent, especially for following the actual intention of the research by the problem. But even if we're not sure, not equals is the best guess. If it's wrong, you might lose a point or two, nothing too major. Well, we have statement of the parameters, we have the actual test we'll run. Not a bad idea, even with the provided significance level, to just say it. Test this at alpha equals 0.05 as just a reminder. And next thing we'll look into is the condition checking. We did a lot of work just building at this table. That makes condition checking a little bit faster for us. Recall, it's not about expected successes. A big confusion because now in chapter 19, just a reminder, this is what you would do for your methods in determining if conditions are met. Take the sample size, the value from the null hypothesis, and just multiply like this. It's probably not even an integer. You'll probably get things like 12.35 and so on. But over here for condition checking, we just want expected successes and failures in both samples, this one and this one, to exceed 5. So let's just list them out. For enhanced diet, has 19, which is greater than or equal to 5. That's what we have to pass on this one. Successes. And 14, which is also greater or equal to 5, failures. So that's our enhanced diet. We get the successes from here. We can get the failures for taking 33 minus the 19. Well, the way we wrote it out, it's just the 14 indicated. And it'll say regular has from over here 15 successes, which exceeds the benchmark. It's greater than or equal to 5. And 15, which is greater or equal to 5 as well for the failures. So that's all we need to show. This means our sample sizes are large enough. We meet the conditions. When you go to do this as an actual homework question, you do have to show the number of successes, the number of failures for both samples, so that we just know we have the right counts. So maybe just a quick reminder, because this is actually an easy part to forget on problems. Not so much the greater than or equal to 5, more about these values here and here. We must show these on homework assignments. But the actual exam questions themselves, like we mentioned before, is going to be less about condition checking, more about using the formulas and making the conclusions. So there's not condition checking elements as much in the actual exams. But for the purpose of the homework and the take-home exam, this is a really important part to take a look at. Let's write here an overall conclusion. The sample sizes N1 and 2 are large enough. So that's a nice part of our condition. But on the other hand, with our conditions, we also needed random samples. How random is this data? More importantly, we needed independent samples. Notice that the counts are a little bit different here. 30 offspring, 33 offspring to 20 parents. Some of these offspring had to have come from the same parent. That makes the data dependent at that point. We have actually some big problems with our data, and it takes a lot of expertise with people, particularly in the biological sciences, to really tease this out, to say, is there dependence here or not? As statisticians, we're not even the right kind of experts here. We need the content area experts to help us out with this one. So if biologists and statisticians work together through this problem and made this experimental design, looking into this outcome, they might have had some arguments, some ways to control and determine if there's independence or not. But we're outsiders looking into what looks like an abstract. This doesn't look good. I would probably say on this problem, randomization, despite the experimental design splitting into groups by random, that was on the parents, not the offspring. So randomization is questionable. The populations themselves, they're independent from one another. The enhanced diet is independent from the regular diet through randomly splitting by randomization the 40 opossums. But within the populations, we have a dependence problem where 33 offspring to 20 parents means there is plenty of offspring from the same parent. That's dependence within the values in the sample itself. Randomization is supposed to protect us against that, and we've lost the ability to do so. So randomization is questionable already. And the observations within both samples appear dependent. Let's add just a quick justification on that, just like we mentioned. Appears dependent since multiple offspring corresponds to the same parent. So there's a lot to think about in this kind of problem. Randomization is questionable means we may not be able to fully commit to our conclusion. We might want to mention this at the end. It's nice to see everything else working out, but there's a lot to think about and discuss on a problem like this one, which makes it a good statistical problem. Not everything is cut and dry, and this is one where there is a good, healthy debate you could have on this kind of problem. Anyone have a take on how you feel about it? Does it feel like we have randomization? Does it feel like the observations could be independent despite the struggles we mentioned? Or do you feel like we should just leave it just like this? Definitely open to different takes and questions on this one. Okay, let's move on to the next part then. But with these kind of problems, sometimes it sits around in your subconscious a while. If you do have a different take, but it's days later, hours later, but you want to share it, don't hesitate to share it with me. I'll come back to this notes, include what you said, and maybe discuss it with the class as well. Just a different way to look into this problem, because it's a pretty controversial problem, maybe our most controversial one out of all the data we've analyzed. But the good news now is, if we're going to move through this part, this is all math basically. We go up to the original data that we have here, now in essentially a data table, and just start maneuvering through our formulas. This part is similar to what the exam 3 is going to feel like, except that I'm not sure how we did that, except that we're not in chapter 20, being the only difference. So I'll move this data table down as we move to the next parts. First thing we want is the pooled sample proportion of successes. We're going to assume the null hypothesis is true. So that means both p hat 1 and p hat 2 are doing the same job, estimating p naught. So let's call this, for the pooled sample proportion of successes, this is confusingly p hat. That's how our author indicates it, not the same one in chapter 19. It's a good idea to just write in the formula right away, because that can resolve the confusion. Places us firmly in the context, 2 samples. So in our problem, x1 is 19, x2 is 15. Sample sizes go 33 and 30. So I'm using just the first parts here. Probably not a good idea to look into the p hat values, because you don't want to take the simplified value. That will mess up the data in a spectacular way. So this looks like 29 plus 34 successes over sample size 63. So that's our value of the statistic. Now, next thing we'll do is go into the standard error. I'll leave that value here in its exact form and just put it in the calculator just exactly like that. Standard error of this p hat is also context sensitive. So we're using this standard error because we use the pool samples proportion of successes. We still call it standard error p hat, but the formula for this one goes square root p hat times 1 minus p hat times 1 over n1. We're bringing in the sample sizes now, plus 1 over n2. If n1 and n2 are equal, this formula would simplify even more, but it has to allow for unequal sample sizes. Just like in this experiment, you can't ensure your samples are always equal. Let's fill in the formula to get 34 over 63 for p hat. 1 minus 34 over 63 for the 1 minus p hat. And then 1 over n1 is 1 over 33. Likewise, 1 over n2, 1 over 30. So we've got the format. We just need to plug this now into a calculator. Usually for this kind of problems, we want 4 significant digits. But I think rounding to the 4 decimal places does that job for these data. So let me throw this now into a calculator. Let's see how we do on this one. So SQRT to call the square root, 34 over 63 times 1 minus 34 over 63 times 1 over 33 plus 1 over 30. It's kind of a weird calculator to use, but just as good as a scientific calculator you might bring to a class setting. Here's the value we get. Standard error is about 0.1257. So with that standard error in place, we're now ready to compute the test statistic. Any questions at all, folks, up to that stage of the mathy section of the problem? Okay, standard error is probably the bigger formula in this section. Test statistic is not too bad. This one is going to be a z-test statistic, indicating we're using the normal distribution. What we go back down is, we're wondering, is the null hypothesis reasonable? How many standard deviations is p hat 1 away from p hat 2? We don't know that exactly, but we can approximate it in terms of the standard error. So we'll divide this by SE p hat. And I think we can go with a new color on this. Let's make this one go green next. So this will then turn into, let's see, p hat 1, we're going back to the original data. So 19 over 33. Subtract from that. P hat 2, let's use the simplified form, 1/2. And then finally, down in the denominator, we just throw in the approximate standard deviations, 0.1257. Now this is going to tell us how many standard deviations away p hat 1 is from p hat 2, how reasonable the null hypothesis really was. Let's do 19 over 33 minus 1/2, divide by 0.1257. And we get this as our test statistic value. To 4 decimal places, we have a 0.6027. But those are in terms of standard deviations. The p hat is away from p hat 2. Let's say that this equals number of standard deviations. P hat 1 is away from p hat 2. Starting to look not good for the Trivers-Willard's hypothesis for this particular experiment, these data, because that's not a lot of standard deviations. This is typical. If the null hypothesis is really true, that could happen a lot, being within 1 standard deviation. It would happen about 68% of the time using the so-called 68 to 95, 99.7 rule. We still want to calculate a p-value, but it doesn't look like our data is significant whatsoever on this problem. Well, let's get the p-value next. To get a clean p-value on this, looks like it's less about the data table. It's more about what hypothesis test did we actually run? We need to figure that out first. So let's say here for the p-value, we selected a right tail test, which then tells us, oops, I think I hit that button again. I was trying to use the up arrow and it wasn't working. I think I just hit the shift key a bunch of times. That upsets Windows in a weird way. But for the right tail test, we have a p-value. It's going to be now just p norm. P norm because we used z. If we used t, we'd have used pt instead. Do p norm. Z goes inside right into that position. So throw in 0.6027. And that's basically it. But recall, if it's a right tail test, we have to control the area, the direction the area is accumulated in. So we need to put in lower dot tail equals false. All caps just because that's my thing I'm trying to do this time with RStudio. It's just a better practice to indicate your booleans as all caps fully written out, either false or true in that way. So this will give us our p-value. That's a really fast statement to run. The syntax is here, so we'll just do directly p norm 0.6027 lower dot tail false, and that's our p-value. It's quite large, but we should expect it with the smallest standard deviation. It's at 0.2733. Once we get that p-value out, our job is to return back, all the way back to this statement. We want both part A and part B, because conclusion on the hypothesis test means we have to mention the parameters, and we have to directly say what we were testing, which is right here. The conclusion is about that alternative hypothesis. There's only two conclusions we can give, like we've mentioned all along. We'll either say we're about to support the alternative hypothesis, or we're going to say we failed to show that it's true. We had alpha set at 0.05. Let's put in this statement here. This is greater than 0.05, which is equal to alpha. And this part means we fail. Let's put greater than or equals to. That's the benchmark where we hit a failure. We failed to reject H naught. So this tells us how our conclusion is going to go right at this step. Any questions at the moment on getting a p-value and making the conclusion here? Okay, this is where we have to again be really, really careful in hypothesis testing. With all this work, culminating the p-value 0.2733, the way we got there was we assumed that's true, that the Trivers-Willard hypothesis is the actual reality for this biological situation. But that doesn't mean if we fail to reject the null hypothesis, we keep on accepting the truth of it. Hypothesis testing is always weird. It's always as a good reminder that even in a court of law that directly mirrors the logic of hypothesis testing, if I'm exonerated from some crime, it was never actually proven in the courts that I was innocent. They just failed to rack up evidence against me. And that's what happened with us. We just don't have enough evidence in support of HA, that alternative hypothesis. So we always go back to reading this out, but what we say in the stop part is what changes. We'll say here, this study fails, coming from right here because we failed to reject the null hypothesis, fails to find significant statistical evidence we can't necessarily say in support of the Trivers-Willard hypothesis, because we were doing something very, very specific. We have to conclude on what the experiment itself actually was. So that's why we have to return to that hypothesis using those parameter values. And after we read out that statement, then we can actually say another extra ancillary statement. In this particular problem, it does not look like the hypothesis is being supported. But we can't make that as a blanket statement. We're addressing the actual specific study itself. So we'll say, fails to find significant statistical evidence that P1, we have to read this out, that the population proportion of male offspring to opossums given an enhanced diet. So I've read out to just this statement right here. Now we'll say is greater than, we're just directly reading this out, is greater than like I spelled that, wrote that weird. There we go, that looks a little bit better, is greater than the proportion of male offspring from parents with My hand is actually getting tired at this point. From parents with a regular diet. Okay, so we read out the alternative hypothesis. You might put in at the 5% significance level. That's totally optional, but it'll tell us what was the benchmark we had to pass for evidence. Didn't really matter. That's a huge p-value. Any practical significance level alpha would have gave us the same conclusion, but still nice to mention that. Then we can say at this point, if we want to, this is optional, this problem is about the Trivers-Willard's hypothesis. We need a lot of repeated testing for that kind of general overarching hypothesis, not just with opossums, and this study itself ought to be replicated. Maybe enhancing the diet for P1 a little bit more so we can separate out the healthier parent statement. But we can stay here just still as an overall emphasis. These data do not support the Trivers Willard's hypothesis. Well, that's the conclusion so far. But we might want to say even more to this problem. The data themselves were messy and we had some trouble understanding randomization. So we might want to say that here as well as just an extra statement. This conclusion, let me put here that the problem continues. This conclusion may be challenged, maybe by Trivers and Willard themselves, who knows? Probably not, but it may be challenged on the basis that the data may not be random nor independent. We have independent populations because of the splitting into an enhanced regular diet. We mean nor independent within the groups. Within the treatment groups. So pretty challenging data. There's lots to say with this, but I feel like a good course on statistical methods should really show you some data where things really go awry. And this is one of those kinds of cases. We can analyze the data, we can get a p-value out, but until we resolve any concern you might have had right here, our conclusion is really just kind of not entirely real at that point, and it could be totally challenged. But it's nice to see that kind of problem and have those sort of discussions. At the end of this kind of problem, I'm going to get rid of that box. At the end of this kind of problem, also recall the big part that we're doing here was we had to directly give a conclusion on the hypothesis test itself, then return to any overarching statement about the original context, that particular hypothesis. But looks like we finalized that particular problem, kind of a long one to get through. Any questions at all, folks, before we close out these notes here? Well, Microsoft really works on it. Okay, let's give Microsoft a chance to figure out how it feels about life. There it goes. And now for the next section, if I can find the thumb drive, here we go. We concluded chapter 20, and now here's the new adventure we're getting into in chapter 21. I don't have a lot of time to start a problem, so what my goal is for the last remaining minutes we have so far, just to give you an overview of what we're about to do, what these methods are going to look like. Because this one is a lot different than what we've seen before. The chi-squared procedure we're about to present only has the hypothesis test. There isn't follow-up confidence intervals that we're providing here, although there are plenty of methods to provide those if you want to dig deeper on this. So we're doing what's considered an overall test, looking for any difference. First, here's some statement about a new probability distribution, the chi-squared distribution. Much like the normal distribution, it's complicated. Much like the t-distribution, it involves a gamma function as well. Here's a gamma function. So to just do one function evaluation on this, to build the curves like you see down here, imagine you're getting that peak value. We'd have to come up with the x value down here, maybe it's 1 or 2, plug it in here, then do this huge wild integration. Then when you integrate this, you also have to integrate the gamma function, which is an improper integral. There's just a huge amount of complexity going on here. So a lot came into place to provide this distribution. The good news for us is we're going to analyze it this way, calling chi-squared directly through RStudio. Much like we say p-norm to call the normal distribution, pt to call the t-distribution, we write p chi-sq for chi-squared to call the chi-squared distribution. And this one highlighted in yellow is the only syntax that's relevant to our hypothesis testing. There's only one kind of test we can give. It'll be probability chi-squared at k minus 1 degrees of freedom greater than or equal to a. A is going to be the test statistic. K is going to be the number of outcomes to our categorical variable. So this first page is really here for the sake of completeness, also to share the syntax we'll use. But a little bit more information on the chi-squared distribution is from that k minus 1. This is maybe the most important part on page 1. What is k? We have a categorical variable, and k is going to be greater or equal to 3 is the number of outcomes in a categorical variable. So if we're looking into 3 categories, we will go here and say, A, your test statistic, 2 degrees of freedom on this test, categories -1, lower dot tail is false. So actually getting the p-value out is pretty remarkable. But also look at what happens. At 4 categories, severely skewed right as a distribution. And there's no central limit theorem that's going to reshape that. This categorical data is just going to keep this shape directly as is. But as the number of categories increases, we're now at 6 categories, it does start to normalize into a more symmetric shape. But becoming symmetric is a slow process. And it's not like we want to increase k. K is the number of outcomes in a categorical variable. It's provided to us. It has to stay exactly as is. But it's interesting to see how these shapes change. So one categorical variable we're going to analyze, let me skip down to this page, is going to be this one. We looked into this problem all the way back into chapter 1. In fact, we even ran the chi-squared procedure on this one. But now we're going to analyze it in earnest. What makes this a chi-squared problem is there is one variable. We formatted this table differently. It was more of a vertical table where we had counts as one column and the outcomes as the other column. This is one variable, and this is going to be, what should we name this variable? About just season. There's 1,361 homicides that were categorized, probably for one particular year. Really old data, you can actually look up this document if you like. I think this is a particular area, and they took a random sample of homicides and just saw where they fell across the season. So season is the variable, and there are 4 outcomes. This tells us k is 4 in this problem when we go to run through it in the chi-squared procedure. So how do we run through this? Essentially, what we need is a distance measure. And there's lots of ways to create a distance. For example, we go back over to, way back over to chapter 2. One way to create a distance between things is this way. A standard deviation formula. This measures the distance between every single observation and its central value in this kind of way. Squares it, makes it positive, divides by n-1. It's not that we're going to use this formula, but the idea behind this formula It's kind of striking in these notes. This is one data table of the counts we actually got. We'll create another data table of the counts we expect when a particular null hypothesis is true. And this is the computation for the distances between the tables. The observed count is what you have down right here. The expected count is kind of like what we did in chapter 19. N times P naught. We're going to do that same exact formula. N is 1361. P naught is going to be 1/4 coming from over here. So we run that same thing. We get expected counts down below. And then we ask ourselves, how far away is the observed counts from the expected counts? Counts we expect when the null hypothesis is true. Chi-squared right here is the test statistic that does this measurement for us. And just for the sake of a temporary screenshot to really look into the two, here's what the standard deviation was doing. Notice the squaring. This is to make sure that this stays as a positive measure. Then we divide by something on each one. This is where the formula's departure from n minus 1. Let's try to achieve the same kind of thing. S squared is a distance measure of how spread apart all of your data is. And chi-squared down below is also a distance measure of how far away this table will be from the other table we get, assuming the null hypothesis is true. So that's the logic of the chi-square test. Again, big departure from what we've done before. This time we don't have a confidence interval. This time there's not very much parallelism between our methods. This is something really completely new as from before. No normal distribution. But we'll look into, again, how this test statistics work. We'll calculate it by scratch, look a little bit into the conditions. But when we come back on, let's say, after taking all review questions on Thursday's class, the 17th, we'll come back up here and really look hard at what's going on with the null hypothesis. It's different, and what's going on with the alternative hypothesis as well. Lots to discuss with chi-squared. There's only 2 examples here. It's all in the details of what we're actually doing that makes this a longer section than it feels like. But any last questions or comments, folks, about chi-square so far? Okay, well, we'll end class a few minutes earlier today. And then just another reminder, we'll take questions in the context of reviewing for exam 3 when we come back on next class. And at the end of those questions, we'll just return back to the chapter 21, moving through those examples. But have a great evening, folks. I'll see you all on the next class.
Would it be possible to get a Word document or exam 3 exercises?
Yeah, absolutely. Word document for this one? Yeah, let me make a quick note on that to make sure it happens. You know, I never have provided Word documents for these. That's a really good point, that sometimes people want to maneuver through these, move things around.
Table exam 3, they're all very small, so I like to print them out.
Gotcha, yeah. So I'll make sure that that gets put in.
Thank you.
Yep, you bet. Thank you.
And I clarified I submits assignment 82.
Gotcha.
I don't think I did, and I apologize for that.
Oh, no worries at all.
Let me quickly get my name on that.
Thanks for getting that one into me.
Thank you for taking it.
Yeah, you bet.
Since I submitted this one last week, Tuesday night, since I forgot to bring it with me.
Oh, gotcha.
And I checked my email because I was looking for something else and noticed I didn't see that I had anything sent to you.
Gotcha.
So I don't think I submitted this to you.
Perfect. I'm really glad you got on the hard copy. Thank you. You know, that actually happens a lot. It's kind of the reason why I don't have a late policy. One thing that happens in this class is people that are doing it on an iPad, iPad is a really weird way of sending emails where you could send something with an attachment, turn off your iPad, and it actually never sends. I get like an email coming through like days later, and the person thought they turned it in on time. So I just decided the late policy doesn't even make sense, the way this class is actually running.
Thank you very much for having
You
me.
betcha, you too.